that's the main thing. So let's see. So are you able to open it now?
Yeah, I got it. I got everything open. It just took me a couple of tries.
Yeah, sometimes that happens. And I know sometimes there are issues like with if you have old cookies and your cache isn't cleared. Because the way Pearson works is it kind of has this proprietary software where it checks to see if you're really the right owner and someone else isn't using your password. And so if it stores an old session, it'll cause trouble. So it's usually not a bad idea to go in every once in a while and just clear your cache, clear your cookies, stuff like that. Okay. All right. So why don't we get started? I'm going to go right into the problems if there aren't any other issues we want to discuss before we begin here. Okay. And let's see. So we got number 9. And go ahead and open that up. And so now we're talking about confidence intervals, right? We're shifting gears. We're going from hypothesis testing to confidence intervals. Okay. And everybody can see my screen?
Yes, I can see your screen.
Good. Sometimes it will go off in the middle of a presentation. Just let me know. We were just talking about software and glitches, and I have about 4 or 5 applications that use my front camera. And sometimes they'll decide not to play well with each other, you know. Okay, so the first question says a blank is a single value used to estimate a population parameter. And so if we think about confidence intervals, right, and what's going on with them, if we took one sample, okay, so we have one sample here, and samples estimate populations, right? And I want to get the single value, the one number from that sample that I think is my best guess as to what the population parameter is. That's going to be the sample estimate, right? So, for example, if my parameter of interest here happens to be a population mean, right? My sample estimate is going to be the sample mean. Or if I'm looking at a population proportion, it's going to be the sample proportion. And so we give a different name to the sample estimate now, because when we're thinking about a confidence interval, okay, what we want to do is we want to plot these values on the real number line. So the value of this sample estimate, this single point, we're now going to give a new name. We're going to call this a point estimate. It's the single point on the number line whose value is our best guess about the population parameter given a sample. Okay, so that's what we're going to call a point estimate. Okay. All right, so one of the things we have to start doing that we haven't emphasized a great deal in the past is we're going to have to start looking at problems and figuring out what type of problem we're looking at. Because again, when we're looking at a confidence interval, right, we could be looking at a confidence interval for pi, the population proportion, or a confidence interval for mu, the population mean. And so the first thing I want to do in these problems is get a handle on what I'm looking at. And I look at this, okay, a drug is used to help prevent blood clots in certain patients, all right? In clinical trials, among a certain number of patients treated with the drug, so many developed adverse reactions of nausea. We want to construct a 95% confidence interval for the portion of adverse reactions. And so when I look at this, I realize that if I have to choose between one of these two possibilities, whether I'm estimating a population proportion or a population mean, I don't see any words, right, like average or mean or anything like that. So I'm going to be working with a population proportion. So proportion of what? Proportion of treated patients who get nausea. So now I understand the problem. Does that make sense? That seem okay? And now we're going to go ahead, we're going to compute that 95% confidence interval. And so one of the reasons why we have to make this decision early on is because when we go to StatCrunch, it's going to affect how we compute things, right? So I'm going to go to StatCrunch here. And one of the decisions I have to make that's conditioned on what parameter I'm looking at is what command I'm going to use. If I was looking at a population mean, a confidence interval for that, I'd choose t-stats, but I'm not. I'm looking for a population proportion. So I'm going to choose proportion stats. I'm looking at one sample. We took one sample of so many people, right? And I'm not given the raw data. I'm given the summary statistics, okay? And now all we have to do is just fill in the blanks. So number of successes. What is my number of successes in my problem here?
Is it the ones that develop the reaction?
Right, that's the number that's in my category of interest. So my population is all the people that I could treat with this new drug. And I have this categorical variable, developed nausea or didn't. My category of interest is develop the adverse reaction of nausea. So I have 164 successes. Notice that success doesn't mean something good, right? I mean, you have nausea. That's not considered a good thing by most people. What it means is that you found the person that's in your category of interest, right? And now my number of observations, that's code word for sample size, right? Go ahead and type in, whoops, 4846, and go down here. And I'm going to choose the 95%, which is the default, just like 5% for alpha when we do a hypothesis test. 95% is the default for a confidence interval, right?
Can I ask a quick question?
Sure.
What is the confidence interval?
So so we're going to actually get to that. That's a really important, and it's a question that's very often misinterpreted, okay? And so I addressed that. Did you have a chance to watch the video lectures? I think I was talking about what, you know, a really good thing to help you prepare so that you kind of have like fertile ground and these seeds of knowledge can germinate, right? Is to kind of have a background coming into this class rather than just, you know, wanting to learn the commands and do the homework. But I think if you go back and watch those, you'll get a much better understanding because this is just a Zoom summary session, right? I think it'll give you a lot better understanding. But I am going to talk about that.
Okay.
You don't have to mess with method, okay? Leave that alone. There are different ways of computing this, but we're just going to leave that. So click on confidence interval, the default's 95%, and there we go. Okay. Now, the point estimate, what is that? That's the sample percentage, right? And so this is going to be my sample proportion, and I'm going to try to cut and paste this. I've had varying successes with cutting and pasting from my math. It worked in 3 decimal places, right? So 0.0334. And that's my sample percentage. So if we go back to this diagram here, right? I took a sample, and here my sample percentage was 3.38%. And that's going to be the center of my confidence interval. So now what I'm going to do is I'm going to throw on 2 endpoints. I'm going to add and subtract this, what we call margin of error. Just like you hear in the news, right? What percentage of people are going to vote for Bozo the Clown, right? 47% plus or minus 2%. That's that margin of error, right? That 47%, that was your point estimate. And you're adding and subtracting, kind of like an error bar, right? And that's going to give us this confidence interval. So the confidence interval is all of these values in here. And if I go back and I look at my output from StatCrunch here, right, I'm going to get, going to be what, 2.88 is my lower limit, okay? The lower limit here is 2.88%, and my upper limit is going to be 3.89%. And so, yeah, what is a confidence interval? So notice that before we estimated the population proportion by a single point. That's why it's called a point estimate. A confidence interval is what we call a an interval estimate. It's the range of values that we think contain the population parameter. So we say that a confidence interval is an interval estimate as opposed to a point estimate. And what this means is it is the interval that we're confident contains our parameter value. We know when we take a sample and we compute the estimate, it's very unlikely to be equal to the population parameter. And even if it was, we wouldn't know, right? That's the whole point of taking a sample. We don't know. And so what we do is we put this error bar and we say, okay, I know it's probably not 3.38%. I'm going to put this error bar, this margin of error around my sample estimate though, and I'm going to say I think that my parameter here, the population proportion, is somewhere in here. But of course we don't know where, right? Does that kind of make sense, that idea?
Yeah, it does.
Excellent, very good. Okay, so now we're going to go ahead, we're going to input the numbers. Okay, so first of all, check we did that right. Okay. And so now they want the margin of error. So there's a lot of different ways you can compute the margin of error, okay? The margin of error, if you look at this picture, there's a couple of ways I could get it. I could take either one of these limits and subtract it from the point estimate. Or I could take the upper limit and the lower limit, subtract them, and this whole interval length is twice the margin of error. So I could do that either way, right? So I'm going to go ahead, I'm going to take the point estimate and subtract it from the upper value, and that'll give me the margin of error. It's usually not a bad idea, although you can do it on your calculator. I like doing it in Excel, and the reason why is I can cut and paste. And one of the reasons why we have to be a little careful when we do this is because we have to watch for round off error. Okay, so if I round my numbers off to too few decimal places, when I do that subtraction, it can cause me to lose significant digits. So I'm just going to go ahead, I'm going to put my upper limit value here, and I'm going to put my, point estimate here. I'm just going to copy and paste those right from StatCrunch. So this is my point estimate. I take that whole thing there. And put this in here. Okay. And then I'm going to take the upper limit because it'll give me a positive number. Okay, that's put it on top and subtract it. And that looks, no, I think it didn't copy it. It copied the same one I had before. There we go. And just blow them all up. And so I'm going to go ahead, I had all my bars scrunched up there. There we go. And now I'm just going to go ahead and subtract the one from the other, right? The upper from the midpoint, and that's going to give me the margin of error right there. Again, one of the reasons I like Excel is because it lets me round everything off, right? I don't have to worry about, not rounding off correctly. 3 decimal places, I got it right there. So I'd like you to go ahead and try that. Let's just make sure that that works out for everybody, okay? Any issues? All right. And now all I have to do is just go ahead and cut and paste my values, right? This will be my lower limit at the bottom and the upper limit at the top. Make sure you get the right, order. Sometimes people get them the wrong way, and then that really causes problems, right? Like on an exam, you're going to just totally miss the problem if you do that. Okay, lower limit, no, 3 decimal places. So 0.034 we said. And then you can go ahead and try that too, just to make sure that we're all on the same page and we're all getting it right. 0.039. There we go. And so what we're saying is we're 95% confident that the true percentage of all treated patients that get nausea is between 3.4% and 3.9%. Hold on, I didn't do the lower limit correctly. I think I copied, I think when I pasted, it still pasted that point estimate. I'm just going to type it in. 0.029. And that's why I give you guys two chances, because it's easy for those sorts of things to go wrong and then you make a mistake and say, oh, what did I do? Oh, for some reason it didn't copy correctly, right? And there we go. So this is one of the most basic calculations that you have to be able to do on the next exam and on the final. So before we move on, anything we want to talk about or look at that isn't working out?
Oh wait, did we do question C, the construct the confidence interval? I was still doing B, so I didn't know if we were doing C.
Yeah, that's exactly right. We did C. So all you're going to do is you're just going to go ahead and copy and paste or type in your lower limit and your upper limit. Okay.
Oh, okay. Duh. Okay. Thank you.
That's okay. That's all right. And if I'm going too fast, just say, hey, I'm a little behind and I can stop a little bit. It's not a big deal. So there was a question, what is the confidence interval? One of the things that happens with people a great deal is they misinterpret the confidence interval. There was a study, can't remember the details offhand. It was given a couple years ago to people though who were research scientists who use statistics. And they asked them, what is the confidence interval? And it was amazing the number of people who responded incorrectly. And there are some subtle things about confidence intervals. I won't lie to you. I mean, there are some difficult things, the reason why even a person who thinks they know statistics might miss it. But nevertheless, the basic ideas are really kind of straightforward. And here's what you want to bear in mind. When you're looking at the confidence interval from a single sample, so you have an actual computed confidence interval. You took real data and you computed it and you have actual numbers. There is no interpretation for the confidence interval, really. All you can say is that you're confident, you believe that the parameter value is within the upper and lower limits, and you can't say anything else. Okay, so here's your lower limit, your upper limit, and you just have to say, I'm confident that my value of pi is somewhere in here. And in this case, I'm 95% confident. So what we would say is that we're 95% confident that the true percentage, that pi is in this confidence interval. Now here's what we can't say. And this is where people make kind of rookie errors. They interpret that 95% as a probability. So they often want to say there's a 95% chance that the value of the parameters in the confidence interval, and that's totally wrong. There is no probability associated with an actual confidence interval computed from a sample. Okay, that's where people mess things up. Now you might say, well, then that's kind of lame, because if there's no interpretation, real interpretation, what does all this mean? So the confidence level, what it actually refers to as is the method. So when we're talking about the method, this is where we can talk about what 95% confident means. So our confidence level, this is the value, say 95% in our problem. This confidence level refers to the reliability of the method. And again, I'm going to refer you back to the videos. But a 95% confidence interval, what it means is you're working with a method that works for 95% of the samples. That is, for 95% of the samples, the confidence interval will actually contain the value of the parameter. So it's a little nuanced, and the book doesn't come out and make this distinction clearly, but it's one that you definitely want to understand. So let's go through these possibilities and see which ones we can rule out. 95% of the sample proportions will fall between the lower and upper bounds. Well, that's false because it's not the proportion that falls within the confidence interval. It's the value of the parameter. And in fact, if you look at your sample proportion, it's always in the confidence interval. It's 100% of the time in the confidence interval. So it's a little unsure what they mean when they're talking about sample proportions, whether it's the one from your sample or from all possible samples you could draw. But either one's wrong, because the confidence level does not refer to the likelihood, okay, when I run this over and over again, that the sample proportions are going to be in there. It's the likelihood that the population proportion is going to be in there. So A is wrong. B, there's a 95% chance. That's totally wrong, okay? As soon as you see 95% chance, that's going to be wrong. And in this case, we can read a little further and we'll see that it's definitely wrong, that the true value of the population parameter will fall between our lower and upper limits. And again, that interpretation for an actual confidence interval is always wrong, okay? What makes this nuanced, and if you look this up or you read more about it, and the reason why the researchers get this wrong is there's something besides a confidence interval called a credibility interval. And this has to do with a different type of statistics we don't talk about. This is a little bit of a digression, but there's a type of statistics called Bayesian statistics. If you get the chance to study it, study it. It's very, very useful. And with Bayesian statistics, we can use this thing called a credibility interval, which is kind of like a confidence interval, but it's different. And it turns out that for credibility intervals, you can make this sort of statement in B, but we can't for a confidence interval using what we call frequentist as opposed to Bayesian statistics. Okay, one has 95% confidence interval, 95% confident that the interval from the lower bound to the upper bound actually does contain the true value of population proportion. That's a true statement. One has 95% confidence that the sample proportions is equal to the population proportion. That's very wrong. The sample proportion is almost never equal to the population proportion. Okay, we have a word in statistics called almost, well, it's actually in mathematics called almost surely, which means that it's true almost 0% of the time. That's definitely wrong. Okay, so that's kind of a long-winded explanation, but does that make sense? Or are there any questions about why some of them seem like they should be true, but they're not? Okay. And here we go. Okay, so let's see. I'd like you to go ahead and read over your problem and see how you would do this. I want you to take a few minutes and read it. Think about how you should do this. Okay, so let's see, what should I do? I'm going to go to StatCrunch, right? And let's see. I can go to what? Population proportion here, proportion stats, one sample with summary, right? And what am I going to put for the number of successes here? How many successes do I have? See, 162 is the big number. That must be my sample size. Is 14 the number of successes I have here? I see 14 down there. What do you think?
Isn't this a t-stat?
Yeah.
Instead, we have to use that, and then we can put in the n and your sample standard deviation and x bar as well.
So you have to read the problem carefully, right? If you just assume it's a population proportion, there's a good chance you're going to get it wrong. You're just going to put in nonsense. And so one of the things that you want to do, and this is one of the things that doesn't fall into the category of a formula, is you want to try to figure out the context, right? I'm going to read over this problem. Am I working with a mean or a proportion? Well, I see the word mean, right? Mean of what? Well, weights, right? What is my population? Newborn girls. So now I understand what mu is actually, right? Mu is the average weight of all newborn girls. The next thing after I get context is I'm going to start to write down what some of these things are, right? N is my sample size. Okay, in this study, X bar is code word for my sample mean, right? And I'm not going to worry about units. The units are consistent. And S is my sample standard deviation, okay? And now it wants us to construct a confidence interval using this information. Now I can go to StatCrunch. I know what to do and what to put in. But just breaking this down, and I think one of the things that, you know, when you're a student, you look at this problem and it's overwhelming. You have all these numbers, plus it's a new problem and you have to understand it. But this is how we make sense. And I have to go through the same process you go through. I've done it longer than you guys have been alive. Okay, I mean, it doesn't take me as long, but my thought process is it has to be the same, right? You have to be able to do this in your mind. If you can't, you're just shooting in the dark. So now let's do this the right way. Okay, t-stats, one sample. And again, I'm not given the raw data set. And now I know what everything is, right? Go ahead and put in my sample mean. Just be a little careful with how you enter things. Notice the order in which they're given is not the order in which you enter them. If you do something really wrong, it's like if you enter nonsense, like if you enter, let's suppose you were really tired or whatever, and you accidentally entered 7.7 for the sample size, StatCrunch is going to tell you, hey, what are you doing? And I'm going to go ahead and click here. And what do I have to do that I haven't done yet? I entered all the information. One last piece of information.
You have to change the confidence interval.
Bingo, 99%. And usually the confidence interval ranges from 90 to 99%, okay? 90, 95, 98, 99. And there we go. And now we just go ahead and copy and paste this, right? Only have to round to one decimal place, so I'm just going to enter it by hand. 31.9 is my lower limit, 35.1 is my upper limit. Okay. And so I'd say that I'm 99% confident that the actual value for the average weight of all newborn girls is between 31.9 and 35.1 HG. Whatever HG is, I think they made a typo in this problem, unless HG is a weird, like hectograms or something, because this is what they usually use for mercury, so I don't know what HG is. But in any case, it is what it is. So does that work out for everyone? Just want to make sure. If you don't, I'd be more than happy to look at what you're doing.
Yeah, it works out.
Excellent. Okay. And so now what it's doing is it's also telling you the results from a different study where we only used 14 values, okay? And what it wants to know is, are the confidence intervals very different? And this is what it's asking. This is not so obvious necessarily, okay? So if we sketch out what we found, in my problem, I found that the answer was between 31.9 and 35.1. So this is my confidence interval. But there was another study with a smaller sample size, right? And it found that the values were between 30.9 and 36.7. And one of the other things that you might want to look at also is that my sample mean here was 33.5, and my sample mean here was 33.8. And it wants to know, are these confidence intervals very different? And the basic idea is that if they overlap significantly, and the word significant is ambiguous here, but in this case, this one's totally contained in the other confidence interval, then no, there's not strong evidence that they're very different. So if they overlap, there's a possibility that the parameter could be in both of them. So they're not giving us inconsistent results. So this is the idea that they want you to understand. Notice that this confidence interval also has a different confidence level, I believe. No, it doesn't, but it has a smaller sample size. So for smaller sample sizes, we expect it to be larger, right? Smaller sample sizes, we have more error in our estimate. So it's going to be larger. So this is not surprising, and it's not inconsistent. So is it evidence that they're very different? No. So I can rule out the last two, right? And because the confidence interval limits are similar, well, similar is kind of subjective, right? Let's look at the other one. Because each confidence interval contains the mean of the other confidence interval. So one of the questions here is which mean? Are they talking about possible population means or the sample means? And again, this is why I give you two choices. So I'm going to say that they are similar. Okay, they overlap, and the ones contained in the other. Let's see how they interpret it. Yeah, okay. And again, this is why I give you two chances. If you get it wrong, and again, the reason why this is ambiguous is because what does similar mean? If I was a student, honestly, this would be a coin toss to me. I won't lie, because how do you determine what is similar? I mean, we expect the lower one to be larger, but how do we know? Well, you could do calculations and kind of justify this a little bit more, but it still wouldn't really answer the question. So it has to be no, and since you have two choices, if the one doesn't work, you try the other one, right? Okay, any questions on that one though before we go further? Let's make sure. All right. So let's see, use the sample data and the confidence level given below to complete parts A through D. A research institute poll asked respondents if they felt vulnerable to identity theft. In the poll, the sample size was 1,093, and X equal to 524 who said yes. Use a 95% confidence interval. Now, sometimes you read these and notice that they didn't use the word mean or proportion, okay? So how do I know if I'm working with a population mean or a population proportion? Or how can I rule out one of them? I mean, how can I rule out I'm not working with a population mean here for my confidence interval? Well, look at the data given, right? If I was being asked to compute a confidence interval for a population mean, I'd have to be given the sample mean and sample standard deviation. But here I'm given the sample size and I'm given the number who fall into one category, right? So this is a categorical variable. Do you feel vulnerable to identity theft, right? That has two answers, yes or no. So this is the number of successes. So you have to kind of puzzle through this. So we'll go ahead and put in our answers here. Do not use the z-scores. Okay, I can't overemphasize that enough. A, it's going to take you 3 times as long to do the problem. There's a good chance you'll get it wrong, and it's not exact anyhow. Okay, so go up here to the proportion stats, one sample, the summary. You can go ahead and enter the number of successes. That's the number that X is equal to, and your sample size. And make sure you get the confidence level correct. When they give you different answers on the multiple choice from MyMathLab, one of the ways they generate those is they compute confidence intervals that have different confidence levels because you might have had it on a problem before. Notice one of the really good things about StatCrunch. I'm gonna go ahead and hit compute. If I want to do a different problem, right, I can just click on edit. But if I have a different confidence level in the last problem than the problem before, I'm going to get the wrong answer, almost surely, right? Well, not almost surely. I am going to get the wrong answer. There's no doubt about it. And so you want to make sure that you always have the right confidence interval. So 95% confidence interval, that's the default. We're good. Point estimate is a sample proportion, right? So you can go ahead and just copy and paste that, right? Sometimes it will ask you to enter it in terms of a percentage, and when it wants percent, it'll put a percent sign here, but I don't see it. So I know they just want a decimal, right? And usually percentages won't have as many decimal places. Usually it's just one decimal place. Everything good so far? Okay. Margin of error, same deal, right? You can do it however you want. You can subtract the upper from the lower and divide by 2. You can subtract the sample proportion from the lower limit or the sample proportion from the upper limit. Either one's fine. And again, I have my handy dandy Excel sheet already open. So all I have to do is just clear this off, cut and paste the new guys, and I'm all set. And my sample proportion, just make sure you get the right numbers. That's one piece of output that StatCrunch, for whatever reason, does not give you. And it's kind of an important one, too. And pull that up. And there we go. Yeah. I'm going to check and make sure I enter the right numbers. That looks good. And margin of error, did I round it off to the right number of decimal places? No, it wants 3. I'm going to go up here and shift that over. And since I don't trust MyMathLab, I'm going to enter the 0 at the end, even though I shouldn't have to, right? I'm still going to do that. Okay. And of course, you already have the confidence interval. So I can just go ahead and enter those values or copy and paste it. And so I'm going to have 0.0450 for my lower limit and 0.509 for my upper limit. Okay. So before we get into the last question, which deals with interpretation, what do we want to talk about in the first 3 parts? What things are we having trouble with? All right, very good. Okay, so I want you to look at the possibilities and tell me which one you think is correct. And look at mine first. If you can do mine, you can do yours. And blow it up a little bit. Tell me which of these 3 statements you think are true. So it looks like D, right? There's a 95% chance Because my confidence interval is supposed to contain the population proportion. It's 95% confidence interval. So there's a 95% chance, right, that my population proportion is going to be in my confidence interval, right?
Right.
Wrong. So remember what we said. When you're computing an actual confidence interval from data, there's no probability that the parameter's in there. Okay, it's a little bit like, I don't want to go into the weeds on this, but it's a little bit like if you have a die. While you have a die in your hand and you're shaking it up, there's a 1 in 6 chance you're going to get a 6 when you put it down on the ground, right? But once you put the die down, there's no more probability. It's either a 6 or it isn't. There's no more probability. Same thing, the same sort of concepts going on with the confidence interval. Before you compute the confidence interval, there is a 95% chance, but once you do it, it's either in there or it's not. There's no more probability. And this is the interpretation that most people get screwed up on. There's no confidence that the sample proportion is equal to the population proportion. In fact, it's probably 0 or very close to 0. Okay, so that's definitely false. And again, the confidence interval has nothing to do with containing the sample proportions. It will always contain your sample proportion 100% of the time. That's the point estimate, smack dab in the middle of the confidence interval. As far as sample proportions from other estimates, no. In fact, it's going to be less than 95% on average. So, process of elimination, we got ourselves C. Okay.
Just curious, if the population proportion does not fall in between, how would there be like a question that would say if it didn't fall between, what would the answer be?
So
out of curiosity.
Yeah, so I mean, if you wanted to, although nobody says this, you could say that you're 5% not confident that the interval contains. But really, the idea here is that you never know. Okay, we never know if our particular confidence interval does or doesn't contain the true parameter value. All we know is we know the reliability of the method. We know that when we use it, 95% of the time it will, but we can never say anything about a specific confidence interval, whether it contains it or it doesn't. We use this ambiguous phrase, 95% confidence. And that 95% has nothing to do with the actual confidence interval you've computed. It has to do with the method, the reliability of the method you use to compute that confidence interval. Does that answer your question though? I just want to make sure. I'm not sure.
Yeah, it does. I was just curious.
Yeah, it's a little tricky. The thing you want to remember is single confidence interval, you always have to use a statement like C. All you can say is use this ambiguous phrase, I'm 95% confident that the parameters in my computed confidence, and someone asks you, what does 95% confident mean? You say, okay, I'm working with a method that works 95% of the time. That's what that means. Okay, very good. All right, so here they're giving us some information, right? So they're giving us the sample mean, the sample standard deviation, the sample size, and they're actually giving us the confidence interval. And it's the wording they use is a little strange, T interval. I think what they mean is that it's an interval they computed with T statistics, the T distribution. This is probably off a TI. So that's probably the reason why, okay? But this is how they're going to denote the confidence interval here. So this is the lower endpoint. And copy and paste that into 2 decimal places. So they're being a little tricky. They give you 3, but they want 2. So you got to read carefully. And 22.15. And if I wanted to, suppose I'm on an exam, I'm like, man, I don't know, I think that's a confidence interval, but I'm not sure. I could go back and actually compute it, right? They don't tell me the confidence level, so I might have to do a little bit of guessing, right? Because I don't know for sure what the confidence level is, but I can still do that. It's not, there aren't that many values that it can be, okay? If I tried that, let's just play around and convince ourselves it's not a figment of my crazed imagination. Okay, I sample standard deviation. It's a long sucker here. I'm just going to copy and paste everything so I don't have any round off error. And my sample size is 50. And I'm going to use the default, which is 95% confidence interval. And let's just check and see and make sure. Sample mean, what did I do? I have something before that, don't I? I have a Q for some reason. Oh. And see, that's what I was saying before. If you do type in something strange, StatCrunch will let you know. It's really good like that. And I look at this, and this looks like what I have. 13.05, 22.15. I done good. Okay. There we go. Identify the best point estimate. And again, the point estimate is the sample estimate. Samples estimate parameters, right? And so it's going to be my 17, in my case, it's 0.59, 598, and when I round that off, I'll get 17.60. Okay. If you have issues with rounding, and sometimes people do, and it's not a big deal, you can actually put this in the StatCrunch and use the rounding tool they have, right? I mean, suppose I'm on an exam and I'm like, man, you know, my brain's getting a little foggy, right? It's been 20 hours, you know, am I on the right track here? You can always do this, right? So I can just, you know, hit how many dozen places I want, something like that. And here it wants 2 decimal places, and I've nailed that. So just little hacks you can use. Margin of error, again, you have your pick, right? You can do it 3 different ways. So here's your confidence interval. Here's your point estimate. So you can do this minus this minus this, take the absolute value, or this minus this, and divide by 2. Whatever is easiest for you. Again, I'm going to do this in Excel because I have everything all set up. So these little Excel things, you know, they can really help you a lot. They're really useful. And I know we don't use Excel. We don't have to use Excel, but it is kind of nice to use if you want to take advantage of some of these things. Watch out for round off. So one of the things you don't want to do in this problem is you don't want to enter 17.6. There's a really good chance that you're going to have some sort of round off error if you do that. Make sure that you use the whole number, okay? You know, it can't hurt, right? Can't hurt, might help. So 4.55.
For question B, can you show me your StatCrunch? Can you show me your values?
For which ones? For the margin of error?
For B.
Yeah. So the point. So the point estimate is just X bar. That's the sample estimate. Nothing to do there. And then all I'm doing for StatCrunch is I'm just, for the margin of errors, I'm just taking the upper limit and I'm subtracting it from the lower limit. I'm sorry. I'm subtracting it from the point estimate.
Okay.
So this upper value minus the midpoint, which is the sample mean. So you can do it 3 different ways, and you'll get the same answer. One of the reasons why we use the standard wall is because the standard wall gives you a symmetric confidence interval. The margin of error is the same on both sides. That's not always true for a confidence interval, by the way, but it's going to be true for the ones that we use. But there are more sophisticated confidence intervals, and I won't go into them, where the margin of error is not the same. The left-handed and the right-handed margin of error are different. We're not going to have to deal with that. Okay. So let's see. It says, in constructing the confidence interval estimate of mu, why is it not necessary to confirm that the sample data appears to be from a population with a normal distribution? That's a really good question. What are they talking about here? I mean, we haven't talked about normal distributions in a while. Remember back when we did hypothesis tests? Hypothesis tests rest on the central limit theorem. They're not magic, right? The same thing is true for a confidence interval. So I strongly suggest you go back to the book and look at the conditions that you need to use a confidence interval, okay, for both the population mean and the population proportion. And you're going to find out that it's pretty much the same as it is for a hypothesis test, right? You needed a random sample for the population mean. And then you had your choice. You could either have a large enough sample size, and usually 30 suffice, right? Or the variable itself that you're looking at would come from a normal distribution, right? And so the question is asking, well, why didn't you check that it came from a normal distribution? And the answer is, I had a large enough sample size. I didn't have to worry about that. And so we got A. Does that make sense? Does that seem reasonable? Okay, very good. All right. Now, this is a problem that threw a lot of people when we did hypothesis testing. So I'm going to go ahead. I'm going to read this. Okay. Construct a 90% confidence interval to estimate the percentage of yellow peas. Oh, okay. I know where to go. I'm going to go to proportion stats, right? And let's see. I go to proportion stats. And let's see. I have the smaller number must be the sample size, so that's 171, right? And 445 must be the sample size. Does that look right? Does that seem okay?
You have to add the 171 to that as well.
Yeah, that's my sample size. So here I have a categorical variable. It has two classes, yellow or green. And yellow is actually my category of interest, right? So I have to go and add those two. And so when I do that, I'm going to get what, 616. Okay, when I go ahead and I add those two, right? Now I'm going to have the right number of observations. So you want to add the 445 and the 171, right? I have to watch also with the confidence level, don't I? Your problem might be different, but my problem, I have 90%. It's set to the default. So success is when I find a yellow pea, 171 out of total 616 peas. All right, good. And so this is one of the reasons why when you're doing these problems, it always helps to kind of look at the context, right? Percentage of what? Percentage of peas that are yellow. What is my population? All peas, right? Okay, so let's see. And it just happens we're working with peas that can only be green or yellow for some reason, right? Okay, so my lower limit here, and you can go ahead and pick off yours. 248. Okay, 37. Okay. All right. So is everyone good so far?
Yes.
All right, very good. Now it says, given, so let's suppose, for example, that you're an omniscient being and you know the percentage is not 25%. Do the results contradict your expectations? So let's look at this a little bit. And again, you'll have different numbers, but here's the logic behind this, right? So I've computed this confidence interval. In my case, it goes from 24.8% all the way up to 30.7%. And I'm told that the actual value is not 25%. So 25% cannot be the value. Okay. Does this result contradict my expectations? Well, no, because the confidence interval is not saying the value is exactly 25%. It's saying it's somewhere in here. So there's tons of values that are not 50%. It could be 30%, right? So there's no contradiction here. Okay. So let's read through these carefully. So let's see. My confidence interval does contain 25%. So it could equal, let me make sure I understand what they're saying here. Yes, the confidence interval does not contain 25%. No, in my case it does, so it can only be this one. No, the confidence interval contains 25%. So the true. Oh, I think what they're asking here, now that I read this a little more carefully, is I think they're referring to the sample percentage. I think this is what they're saying. Let's check and make sure that my interpretation is correct. Yeah. The way that this problem is worded is kind of unusual. Generally what you're trying to do, so let me explain what they're trying to do here. What they're usually trying to do is this. When you think about a confidence interval, one of the things that I talk about in the video is that a confidence interval is also equivalent to a two-tailed hypothesis test. So if I look at my confidence interval here, and I were to run a two-tailed hypothesis test with any value in here, I would fail to reject the null. Okay, so if I chose any value, mu naught is any value in here. And of course the alternative, the null is that mu is equal to mu naught, I would fail to reject the null. Okay, so here I would fail to reject. However, if on the other hand, I chose a value that was outside the confidence interval, I would reject the null. And that's kind of what they're saying here, okay? So because 25% is in my confidence interval, it could be a possible percentage, any of these values. And there is no way of saying, oh, this one's like really close to the edge, so it's less likely. It doesn't work that way. They're all equally likely in our eyes at this point. So any value in here can be the possible percentage. And that's the whole point of what a confidence interval does, right? It gives us a range of values, and any of those values could be the population parameter. Okay, this is a problem similar to the last one where we're looking at two confidence intervals and they're going to overlap. So first we have a data set that includes 109 body temperatures of healthy adult males. We'll call the mean and standard deviation. And we want to go ahead and construct a 99% confidence interval for that. Okay, so we go back to StatCrunch. And I go to T-Stats. And all I have to do is just edit it, right? And let's see, my sample mean was 98.2. And my sample standard deviation was 0.68. I'm sorry, about 0.62. Okay, and my sample size was 109. I'm going to compute a 99% confidence interval. So 99% is the widest confidence interval we're going to compute. And the higher the confidence, if we want to be more confident that our interval contains the parameter value, what do? We have to make it wider, right? And if you go back and watch the videos, you'll understand the mathematics for why that works out that way. And so there's our upper and our lower limit, right? 98.044. and 98.356. Okay. So now they're going to ask, what about the use of 98.6 as the mean body temperature? Let's look at our results. Okay. Based on our study, we say that we think the actual value for the average body temperature is between 98.044 all the way up to 98.356. And so they want to know, what about 98.6? Should we use that as the average? Would this be you know, a good value to use? What do you think? Based on our data. Well, no, right? I mean, we're saying that we think the true value for the average is one of these values, not 98.6. So it doesn't lie in our confidence interval. So we wouldn't think that that's the average body temperature, right? Okay. Does that make sense?
Yes.
And so what does it actually suggest? Well, if these are all the values that the average could take, they all lie below 98.6. So it's suggesting that it's significantly lower than 98.6, because all the possible values lie below 98.6, right? All right, very good. They like these sorts of problems here where, like, you know, someone thinks they're psychic or they guess or whatever, right? And the reason why is because they're comparing that with, you know, a coin flip or a random guess, right? So let's see, in a science fair project, Emily conducted an experiment in which she tested professional touch therapists to see if they could sense her energy field, whatever that is, right? She flipped a coin to select either her right hand or her left hand, and then she asked the therapist to identify the selected hand by placing their hand just under Emily's hand without seeing it and without touching it. Okay. Among those 334 trials, the touch therapists were correct 156 times. So what we're getting at here is they want to determine what percentage of times the touch therapist could be correct, right, from the entire population. Okay. So given that Emily used a coin toss to select either right or left hand, now that part's actually important, because what that's saying is that these were randomly selected values, okay? In other words, if a person did it themselves, they might choose a pattern, right? I might choose right, left, left, right. See, Emily here could get 8 right hands in a row. It's unlikely, but it could happen, right? Because she's randomly flipping the coin. So that's what they're getting at. What proportion of correct responses would be expected if the touch therapist made random guesses? Okay, so we would expect 50%, right? In other words, if I flip a coin and I don't show you which side came up, and I ask you to tell me, and you're like a psychic or whatever they are, right? But you're actually guessing, you're going to be right 50% of the time. So we know that's the right answer. And they're not giving percentage, so it's going to be an estimate. All right. So now we want to go ahead and look at the data and say, does the data indicate that they're guessing? And if 50% in the confidence interval, we can't rule that out, right? If they're really guessing, they should have a much higher percentage, and their entire confidence interval should fall above 50%, just like our example here with the body temperatures, right? So let's go ahead and see what StatCrunch has to say. I'm going to put in my numbers here. One sample proportion. Okay. Number of successes, they were correct, 156. 334. And you can see they're actually correct less than half the time. So we already know that, they're definitely not psychic or whatever they say they are, right? The point estimate, I'm going to compute the confidence interval. I could do it just by dividing 156 by 334, but I get it from this anyhow, right? So it's about 46.7%, so 0.467. Okay. And now they're going to have us compute a confidence interval. So we did a 90, and it just happens that it's set to 95%, right? So I'm okay. So I'm going to pick off that 0.422. And the upper limit's 0.512. So go ahead and try that. Make sure that's working out for you then. Okay. Well, let me see, what did I do wrong? I did 95%. Make sure I entered the numbers correctly here. So when you get something that's not correct, first thing you do, let's look at our input. So they were correct 156 times. That's what I'm interested in, my category of interest. 334. Notice I didn't change the confidence level. There we go. So when you get a wrong answer, and this is why I give you 2 chances, because it's easy to screw that up, right? So now it's 0.414. And 0.521. All right, there you go. Okay. So sometimes students will say stuff like, the StatCrunch isn't working properly. StatCrunch works fine. It never makes an error. Okay, computers don't make errors. It's human beings that enter the stuff, right? We're the ones that make errors.
I have a question.
Yeah, shoot.
For question B, why? I don't know if you explained it, but why is the confidence interval 90%?
It isn't, and that's why I got the wrong error. That's why I got the wrong answer, right?
But you got on B you did 90%, and then on C you did 95%.
And the reason why is because the point estimate has nothing to do with the confidence interval. It's just computing the sample estimate. That's going to be the same. So one of the things you want to understand, this is an important point, is that when you compute a confidence interval, the sample percentage is always in the center. So this is a 99% confidence interval, a 95% confidence interval, a 90% confidence interval. But the sample percentage, which is what I needed to compute, I can compute for any confidence level. I automatically get that. Does that make sense?
Kinda. I probably need a better explanation.
So here's the point. No matter what the confidence interval is, what are they asking for? They're asking for the best point estimate. They're asking for the sample percentage, right? Well, the sample percentage is always in any confidence interval. It's smack dab at the center. So whether I used a 99%, a 95%, a 90, a 12% confidence interval, it wouldn't matter. The point estimate, which is the sample percentage, is always in there. So I can do this calculation with any confidence level. And the point estimate, the sample percentage, is always the same.
Okay, that makes sense. I'm getting it now.
Excellent. Okay, so what do these results suggest about the ability of touch therapists to select the correct hand? Well, 50% is in there. Okay, so let's kind of go through the possibilities. Since the lower confidence interval is below 50%, there does not appear to be sufficient evidence that they can correctly select. Okay, that's one option. Let's see. Since the confidence interval is not entirely below 50%, there appears to be evidence that they can select the correct hands. They're not saying it's totally below, 50% is in there. Since the confidence interval is not entirely above 50%, there does not appear to be sufficient evidence that the touch therapist can select the correct hand by sensing the energy fields. And since the upper confidence is above 50%, there appears to be evidence. So here's where they're going with this. You read these and it's like, they all seem kind of reasonable, but here's the idea. Here's 50%. And if they were really psychic, or whatever the name is they use for themselves, the entire confidence interval would have to be above 50%. So this is if they had some sort of whatever, like, ability to sense whatever it is. It would have to be above 50%. In other words, the population percentage, which we think is in here, would have to be greater. In other words, this would be greater than guessing, okay? That's what they're kind of getting at here. Notice that when the confidence interval contains 50%, like it does here, you can't really conclude anything, a definitive, because some of the values are above 50%, some of them are below. Okay. So all we can say is that there's not sufficient evidence to claim that they are, because what we'd have to do to claim that they are is we'd have to have that entire confidence interval above 50%. That's where they're going with that. So it would have to be C. Okay. The fact that 50% is in there doesn't really tell you anything, but it's the fact that the entire confidence interval is not above 50% tells you that there's not strong evidence that they are. Okay, check that. There we go. Okay. This problem I wanted to do because I wanted to show you how to do confidence intervals from a data set. Okay. So here it says refer to the accompanying data set and construct a 95% confidence interval estimate for the mean pulse rates of adult females. Then do the same for males and compare the results. So we have a quantitative, the mean, right? What is it? Mean pulse of what? Mean pulse of all, either females and males. So let's go ahead and open this up in StatCrunch. So we can save ourselves some work. And now I'm going to compute a 95% confidence interval. And where this differs from what we've been doing before is we're going to use t-stats in one sample. But now notice we're not given the sample mean and we're not given the sample standard deviation. We're given the raw data. You can actually click both of these at the same time. If you click on one and hold down Control and click on the other. And so I like doing that because it makes it easy for me, and I'm lazy and I don't want to do things more than once. I don't have to. And go ahead and hit that. And it gives you both confidence intervals. StatCrunch is super cool. I mean, there's a lot of really nice things about it. Okay, so back to our regularly scheduled program here. So we have our data set. We're done with that. And now it wants the confidence interval for females. I'm just going to pick off, right? Means nothing new here. Just pick off, round it to one decimal place. Mm, 2.5 and 70.4. Okay. So go ahead and do that. Make sure that you're getting it also. Just to, so let's see, what did I do? It's 95% confidence interval, right? Let's see. Yeah. Oh, I put the males first. So so you have to watch. So again, this is why I give you guys two possibilities. It's very nice, but you also have to watch what's going on here. So what did I do? I entered the one for males and not females, right? So I got to go back and be a little more careful here. And we're going to see later on, actually, this is a big deal when we start to deal with differences between populations. So this is a good thing to start to become aware of, okay? I'm gonna do it again real quick here. Oh, I threw away my data set. Sorry about that. There we go. I probably have it open in another table, but that's okay. T-stats, one sample with data. I'm going to click females first, so I don't make that stupid mistake, right? 95%. And there we go. Okay. Now we got it. Okay. Now females are first, and that's the way it is in real life too, right? So enter that 71.7 and 80.1. So when you get something wrong, that's a sign, hey, I probably input it. It's probably you. And then I can go ahead and do the same for males, right? And it's going to ask if they're different. And what I'm going to be looking for is I'm going to be looking to see if they overlap, right? And if they overlap, we're going to say that there's not strong evidence that they're significantly different, because they could have the same mean since their values are going to overlap. And I believe in most of these problems they do, but let's check it out. Oh, come on. 62.5 for the males, 70.4, 71.7, and 80.1. And it's 1 decimal place for both. And it's 95% confidence interval. Okay. What did I do here? Oh, I have a comma rather than a decimal point. Format count. There we go. Excellent. Okay. And so now they're going to ask if they're going to ask you to compare the results. You're going to see if they overlap. Here they don't overlap at all. And so this is evidence that females are going to have a higher pulse rate than males, because the entire confidence interval, you can see just by looking at the numbers, the entire confidence interval for females lies above males. Okay. Okay, we're pretty much at the end. Do we have any questions we want to talk about though before we finish up here?
No, I just have to do the reading and watch the videos, and I think I'll be all right.
Excellent. And there are more problems. Again, I'm going to keep these open during the exam. So we didn't finish them all. We only got 9 of 16. So when you come exam time, you'll have lots of new problems that you can try, and it'll be like a fresh problem set. And hopefully that will help you. So
I have one question about, I know you had said that you were considering curving exam 2. Are you still going to do that?
I'm not going to consider it. I'm going to do it. And as soon as I get all of the exam scores in, which I believe a few people have an extension still out, I'll probably post that over the weekend, along with some other relevant information that I know people will be interested in about with grades, right?
Yeah. All right. Thank you so much.
Absolutely. All right.
One question. With the curve, are you also going to add in like the extra credit points you mentioned?
I'm sorry?
With you said you're going to add in the curve, but are you also going to add in the extra credit points that other people have earned?
No, and that's one of the things I'm going to talk about, actually, how I'm going to add in the extra credit. I can kind of add them in wherever I want them. I usually keep them out till the end, though. But when I send out the announcement, which I'll probably send out either Friday night or Saturday, I'll explain how the extra credit. The extra credit points, they generally don't count for much. I mean, each time you get extra credit, it's 2 points out of 1,000, so that's 0.2%. Usually what I do is I add it to the final. Initially, I said I was going to add it to participation and engagement, but it turns out it's a little tricky to do for every person because there are dropped assignments and stuff like that. So it's easier just to add it to a static assignment that can't be dropped. And I could add it to the exam. It's like 6 of one, half a dozen of another. If you guys want me to, I'll add it to the exam. Usually I do it at the end because people accumulate them as they go along. And so at the end, you got this nice little, it's kind of like Christmas came early. You got this nice little stash of extra credit points for some people. Okay.
I need it.
All right. Good deal. Okay. I will see you guys later on then.
All right. Thanks, Professor. Have a good
All right.
week.
Thank you.
Okay. You too. Take care.